Hello and welcome back. We are starting on our topic around abstract data types. Let me make sure I've got all my stuff set up properly. Don't need to record a video with no sound or anything like that. Okay, so we have two main learning goals here that are going to span both of our videos. This first video is about differentiating between an abstract data type and a data structure and understanding their differences and when to use which word effectively. And then the next video is going to be on implementing stacks and queues, which are two different abstract data types, and we're going to do them using linked list data structures so that we can get some more practice with linked lists and see some different ways to potentially implement some linked lists. Okay, so first off, let's talk about the term abstraction. So in the previous unit, we were learning about interfaces, which described basically what a class is able to do, what the behaviors are, without actually knowing how it's doing those things. So our interfaces are just one tool that allow us to focus on what's important in a context and ignore the details. So we're going to learn about some other ways to focus on our contexts and different ways to do so in Java as well as other programming languages in future courses. But in this course, we focus on interfaces and the kind of power that they bring us. So this idea of ignoring details, but focusing on what an object could do, what a data structure can do, is called abstraction. So we're abstracting away all of the details and we're clumping it all together in this abstract type. This allows us to build our systems out of complex components without getting lost in all the minutia of technical details and implementation and debugging and all of those messy things that come with coding. Okay, so our ability to write programs in general already relies on this idea of abstractions, right? We've talked about this one already before. We've talked about how we can write code like system.out.println, and we know what will happen, but we don't actually know what will happen. Like we don't actually know what is happening, how it's happening. We just know that when we type that out, we're going to get something in our console. Just like we think that maybe the computer uses electricity and ones and zeros and some other magic. I don't know. Some things happen underneath the computer hood, right inside the motherboard and everywhere else in the computer parts. And at the end, we get output, right? We get output at the very end. So another example of this is way back at the very beginning of our course, we made that person list class where we could add and remove people from the list and do whatever else we wanted to be able to do with it. So we actually made a list of students or a list of children or a list of friends or all these other things that we could do when it came to things we want to be able to do with a list of people. Now, we didn't actually set up a proper abstraction for it at the time, but we have made proper abstraction since then, like in the previous video, when we actually introduced the list interface and talked about how we could turn our list of students, list of people, array list, linked list, and all these other things into proper data types based on these abstract interfaces. And really everything that we do in computer science has some level of abstraction to it. So I don't know, there's this meme that's going around that has gone around. I don't think it's new, where like there's a person, like there's an astronaut looking at Earth saying something about what they see, and then the next astronaut back is saying, "Oh, it always has been." Um, anyway, I don't know. That's the meme. Know your meme dot whatever. There's a website that like tells you about memes. Anyway, I made this one because it's really important that we understand the nuances of this joke here. Because when Java has been doing, like us as students learning Java, we realize everything we've been doing has been an abstraction, right? How we're interacting with the console, how we do our file input output, how strings are being manipulated are actually being stored as individual characters. All of that, minutia, all that technical details have been abstracted away for us so that we can just easily say dot output, dot read line, dot length. And we haven't had to worry about all the implementation details that Java hides from us, right? So it's always been abstract. So our very first astronaut here says it's all an abstraction with Java. And then when we take one step back, we realize that there's something called assembly code that lives underneath Java that makes our program run. And so this astronaut is saying it always has been. And then we take one step back, and this astronaut knows that that's always been abstraction because assembly code is built on like machine byte code, like zeros and ones. And then it goes even one step further because all of our software engineers, all of our computer engineers out there are going to say it always has been an abstraction because this language, Java, which is built on assembly, which is built on zeros and ones, is just transistors and electricity just flitting back and forth across a motherboard. So that's sort of the crazy abstraction worlds joke that I have going for me here. So when we think about this abstraction, a really good example is to think about abstraction as like an opaque box. So just a box where we can't see what's going on inside. So we know that we're going to put something in, we know that something is going to happen inside, and we know output is going to come out. And typically we can describe what input is going in and what the expected output should be without having to say what is going on inside. Just like when we flip back here and we think about something like system.out.println, and we can say what the input is going to be, we can say what we expect the output to be, but we don't actually know how it happens, and that's on purpose. It's abstracted away on purpose, right? Same with the sort function that we saw in the previous topic, collections.sort. From the name, we know it's going to sort our data. In fact, we can even define how we want it to sort our data. We can tell it by what properties, by what attributes we want it to consider, but we don't actually know what sorting function it uses. We know that there's something like 43 different sorting functions that exist out there, and we have no idea which one is being used here, and it doesn't matter. We just need to know what our input is and what we can expect to come out. Everything else can be abstract and should be to save our brains. So we can apply this concept to the techniques that our programmer is using to store data. So rather than just thinking about it as input output and some kind of algorithm running in the middle, some kind of processing happening in the middle, we can apply this exact same concept to how we store our data, not just how we process it. A data abstraction is a description of a data storage according to the organization of the data and the operations we can perform on it. So basically, we want to give our data structure or data type, pardon me, our abstract data type, a name that describes how the data is organized, right? And we want to give it an interface, how we're going to interact with that information. So let's once again think about the list interface that we introduced in the previous video. That is an abstract data type. We can't actually do anything with the list as its own. We can't instantiate the list. We can't make a new instance of the list class because the list describes how the data is organized. It is a sequence of data collected all together. And we get an interface of how we can use it, and that is what the list interface is. So list is an abstract data type because it is a data type that we can declare, and it's abstract because we cannot say the new keyword on it, and it's an abstract data type or an ADT because it's an interface. It tells us how we can interact with lists that use this interface. An array list is a data structure. A linked list is a data structure. A list is the abstract data type that sits on top of those. Let's think about this example here as a family tree. Imagine for a second that we were going to try and program a family tree. And this is something that you're going to see in 2140 in the next course, in Comp 2140. So how would we store this data? First of all, who cares? Second of all, who even knows, right? Again, implementation of this, you're going to see next year. What are some things that you could do with a family tree, though, if we think about it in the most physical form? We could give birth to children or adopt children, so we can add children to this tree. Maybe we could remove children from this tree if anybody's a Harry Potter fan and we think about the big like Black family family tree and how like the mom would like burn the kids off who mixed blood or whatever else. Starting to get really Harry Potter specific, but they could remove children from their family tree, right? We could connect family members, so we could use it as a way to like figure out who our parents are or our great grandparents are or our cousins are. We could add these marriage or divorce connections. There's lots of things that we can do with it. So we could have a family tree data type. It's totally abstract. There is no family tree data type by default in Java, right? That's something we would have to choose how we want to implement. But we can say, okay, let's make an interface called family tree. These are the things you can do with it. And then somebody who implements the interface would actually go in and decide how to make these implementation choices. So an abstract data type, or often abbreviated to ADT, is a particular type of data abstraction. So abstract data types are type of data abstraction. There are other ways to do data abstractions. We're talking about abstract data types right now. The ADT list, the one that we just saw, is one that we've been using throughout this course and we didn't even realize it. Now we know that array lists are actually implementing this and using it. And when we make our own linked list, we could be using it. We could be saying linked list implements list and then force ourselves to implement all of those methods that we saw in the previous video. The data in a list is organized sequentially. It is in some sort of a sequence order, as opposed to something like a hash map that you'll see next year. Those aren't sequentially organized. It doesn't necessarily mean that the data is being stored sequentially. It just is being organized in a way that we can say there is a first element, a second element, a third element, etc. Something that we cannot always do with other types of data sets. But we can do that here. So often with lists, operations include things like adding, getting, setting, removing, dot size, finding elements, index of, whatever it might be, right? Contains, matches, equals. Those are all the different things. Those are all different operations that we can do on lists. So when we implement the list interface, when we utilize that abstract data type, we find ourselves being forced to implement all of these operations. So we've actually already looked at this link here. We looked at it in the previous video. When we look at the list interface, we can see what is available to us. So the name and the operations of an abstract data type form that public interface, just like our family tree example, just like the very real list example. And then the private implementation is what's implementing that interface. That is, the private implementation is what's actually using a data structure to do the work. So whether we use an array list, a linked list, a role-based list, a sequential list, whatever all those other options were, or more, it just depends on how we want to implement it. And when you do 2140 in the summer, next year, next fall, whatever it might be, you're going to learn about a lot of abstract data types and how they're built. And they're all built on arrays, array lists, and linked lists. And there's just different ways of connecting them in order to build out these abstract data types. So let's talk about an idea here for a second. Let's talk about an ordered list. An ordered list is going to guarantee sorted order always. So this is not the same as a list. This doesn't fit underneath the abstract data type list. This isn't an implementation of a list because lists allow us to do things like add or set in any spot that we want. But an ordered list is going to restrict that. List has set, and set can break that ordered list implementation. So these operations will be slightly different. So if we're going to make our own ADT ordered list, we can still have things like get, remove, size, and find, but it doesn't make sense for there to be an add. That being said, we do need to get data in there somehow, and what we would probably have is an insert. And then the insert operation can ensure that the ordered position is maintained. So let's just take a look at what we might want to write for this code. So we are talking about, let's make a new folder here, and this folder is going to open, is not going to open. Remove this one for a second. Hey, just remove. Just disappear for a second, please. There we go. Remove from workspace. There we go. Okay, let's open a folder. Let's go ahead into our my desktop where I like to throw all my code when I'm doing these videos. And let's do an ordered list ADT example. And this will be our folder. We'll go ahead, we'll open that, and let's make a new file. And this is going to be our ordered list. Now, again, a reminder that the abstract data type ordered list is actually going to be an interface. It's not a class. It's going to be an interface. So this is going to be the abstract data type. And then we're going to also have, let me just move my meeting controls, the different things that we can do with it. So for example, we could do a get. Now, at this moment in time, we don't know what kind of data we want to store in there, but all data falls under object. So we could just say get like this, and we could get any position. There's no reason why we can't just see what position something is at. That makes sense. It can return null if no, not present. No, if invalid index. Really, it should throw an exception, but that's fine. So that's get. Let's see what else we said. Remove, size, and find, and insert. So we're going to have a remove, which also usually would return the object that gets removed. There's actually two different ways to do the remove, as we know. This one will return null if not exists. We could also do a remove by index or by object. So go looking for a specific object to remove. And in that scenario, we would return true if removed or false if not exists. Let me just move this out of the way so we can see more words here. And then we said size, find, and insert. Sorry, I totally forgot. Int size will get us the size of our ordered list. Find is kind of a tricky one. Like, what should find actually do? Does it return the index? Then that's more of like an index of. I feel like a find is more of like a contains. So I'm going to rename this. I'm going to do like a contains that will return true if found and false otherwise. And then I'm also going to do like an index of an object. And this one is going to, return object index if exists -1 otherwise. And then we also said we want to have an insert. An insert should probably return a Boolean to say true or false if it got inserted. Why wouldn't it get inserted? Now we can just say void. And this will be our insert, and we're going to insert a given object. And this is going to insert the object given, insert the object into correct sorted order, whatever that order might be for our ordered list. Perfect. So this gives us everything we need to keep an ordered list nice and sorted. We could implement comparable to help us with this as well. So then like collections.sort on an ordered list would also work. But that can get really tricky here. Like it is a thing that we could do, but it's kind of outside the scope of the course to worry about writing making this whole thing also use comparable. Because remember, this is an interface. So that might be a little bit outside the course. That's okay. This is our abstract data type, though. Ordered list abstract data type, totally created and lovely. We're not using it yet, but we now have an example of this ordered list interface. I wrote object list, but really it's an ordered list interface. So now what we can actually go and do is we can implement this. We should create let's actually do this one here, ordered number array list implementation. And then you're going to take a pause and you're going to go ahead and do it as a linked list. So did I upload helper code for this as well? No, but I will. I will as part of, I couldn't remember if I specified it, but we'll do it now. So that's okay. Okay, so we're going to go here. We're going to make a new file, main.java. Let's just get our main method up and running here. And it's going to have a main. And it's going to have an ordered list in it, OL. And we have to say OL equals something. We're going to have to like instantiate our ordered list, right? And we said we're going to make an ordered list array list, but I haven't done it yet. So I'm just going to leave this as dots so that like it doesn't do anything. And then we're just going to make them all integers just to make our life easier. Does that make our life easier? Yes, I feel like it does. So we're just going to say I less than 0. We're going to insert 20 random integers. Sure. Integer rand is going to be a random integer between 0 and like 200. I'm just making this up. Who has any idea? Not me. let's say I'm going to do good programming practices. Final int max random. It's going to be 200. I'm super good coder. Make this +1. So then that way this actually represents the maximum this way. And then we can just say ordered list dot insert integer. Oh, rand. And we're just going to start adding like random integers in. That makes sense. We're also going to need some way of like printing out all of our information. And I think we'll just do that through the interface also, where I'll just make a void print list method. That'll be required. And then that way over here, I can just say ol.printlist, and it will print out our list appropriately. Fantastic. So that looks great. This is nothing right now. We're about to make it because we are going to make an ordered, nope, that's not right. An ordered list array list is going to be our implementation that we decided. So that's what we're going to call this class. And thanks to Visual Studio, I can say quick fix, create class, and it'll make me a brand new file right there, public class ordered list. And we are going to implement our abstract data type ordered list. And we said this is going to be an array list of objects. I'm choosing for it to be integers on the front, but objects here is just fine. Array list, new array list of type object. Okay, so two things have to happen. First is I have to implement this array list. The second here is going to be that I have to now implement all these methods that I'm requiring. So I'll go ahead and click quick fix. I'm going to also want a constructor. And the constructor is going to do this. I made a little mistake here. We don't set that there. We set it in there. There we go. Okay, so now I can actually do these. Well, what does this get actually look like? We're just going to return al.get at I. Simple enough. It's called index. Simple enough. Okay, same with the remove. If we actually manage to remove something, we can just say, where did it go? Oh, sorry, this is so weird that it has like this up here. It's messing with me. Array list dot remove our index. There we go. Here, this one is going to remove by the data type. So we can say array list return array list dot remove this object. Is that going to like it? It might not. Oh yeah, it's fine with that. Okay, cool. Here we're just going to return array list dot size. Here we're going to return the linked list one is going to be way harder. Sorry, not harder, just like more work. Contains, because you're making your own linked list. And so these methods don't already exist. You'll have to like actually do some implementation in here. Right now, I can just call the array list version of everything. I can do index of array list dot index of my object. Insert. This one I actually have to do. This is going to be the ordered insert, which I'll do in a second, and my print list, where I'm going to go through every element in my list for each integer I. Oh, no, it's an object. Whoops. Object O in my list. I can just print out O. Now, if I want to do my insert here, I'm probably going to need to make a loop. And it's an array list. That's fine. Insert should be pretty straightforward. I can do this. I can say my array list dot size, I++, and I can just look for the position that I need. In fact, I can say if, for insert, I can say Boolean position found is equal to false. And I can say while we have not found this position, we can just go looking for it. And we'll know if this is super tricky. It's not that tricky. Dot get at I dot compare to our object is less greater than 0. That feels right-ish. If it's greater than 0, let's do it like this. Oh, that won't work. I'll talk about why in a second. But if we find the right spot, position found equals true. And we can also do our insert like right here so that we don't lose the position. We can just say al.add into our linked list at this position, this object. Okay, so by doing it this way, we avoid letting anybody put something like add something in, which is kind of nice. And now we're going to fix this little error that we've got right here. So let's just dig into why this isn't working here for a second, why we're getting this red line when it comes to our array list.getAtI. So this is an object.compare to at another object, and why that actually isn't running for us. So what's really happening here is that this is the object, capital O object, right? So we're talking about the Java object class. And we've seen this class a few times, like when we were talking about .equals methods and .toStrings, but there actually isn't a .compare to method on object. It doesn't exist. This method doesn't exist on object, and object does not implement the interface comparable, obviously, because if it did, it would have a compare to. So since it doesn't have a compare to, this is not going to work like this. So what could we do instead? Well, it depends. We have a few different design choices effectively. Since we wanted to keep everything capital O object here, throughout our whole thing, something we can do in here is we can just do a quick check to see what type of object it is, and then run this appropriately if it needs to. Now, because we are writing our code in a way that we know we're going to be, where's my main? Right here. We're going to be storing integers. We can go ahead and cast what's coming in as an integer. Now, integer does implement the compare to interface, capital I integer, it does. So it has a compare to method. Now, if we want to be really safe about this, which I think we do and we should be calling, let me just think about this for a second. We should be casting this value to an integer. So let's go ahead and make an integer cur value, and we are going to start it off as null. Is that going to be fine? It'll be fine for right now, but it's not going to be great programming practices. What we want to do is we effectively want to say, if the element right here, I want to make sure I get the right things here, is an instance of the class integer, we can go ahead and say cur value is going to be equal to a cast of this. This is a safe cast because before we do the cast, we're making sure that we are a type of integer. So you could just do this directly, but if you want to do it safely, you want to use that instance of keyword with this if statement here. We could even do it in a ternary if statement, which basically means turning this if statement right here. You put the whole thing here and you ask it as a question. You say, is this element an instance of integer? If it is, what do we do? Well, if it is, we're going to go ahead and cast it. And if it's not, we're going to say null. And this is called a ternary if statement, where we can do the assignment of cur val with the if statement all in one line. We ask the question, if this is true, we're going to do this. Then you say colon, what you'll do otherwise. So that's a ternary if statement, and it's just a shorthand there. It's a ternary conditional, I suppose. So providing that that actually is indeed an instance of integer, which in our case we know it will be since we're writing our own code in this way, we can just go ahead and do this now. We can say curval.compare to, and we should do the same thing for O, where we're also going to check to make sure that O is an integer, right? And again, if they weren't integers, we'd have to find a way to handle that situation. This code doesn't handle the situation well if it's not an integer. This code is just going to just go for it, and we'll end up with all sorts of exceptions. So the only reason that this is going to work right now is because I know from main I am definitely passing in integers, but a lot more work would need to happen if I wasn't sure that an integer was going to be what was coming in here. But in this example, I do. So now I can go ahead and say integer curval, integer oval, no problem, compare them, get the correct position if it's found, add it in the right spot, and then come back out, and this will break out because position found is true, and our code can stop. So now our ordered insert is actually written here. So I'm going to go ahead and save that. Right here, we're going to just print out our list and make sure that everything is being inserted in the right order. That's what we're checking here. So if I go ahead and quick run, see if we got any errors. I have no idea. Oh, nothing ran. Nothing happened. Public static void main. Oh well. Oh well, print list. What does print list do? Did I make a print list? I did a print list. Object O, print line each one. Oh, cool. Something here happened. Always love when that is the case. Let's try one more time and just see what is going on here. This is our ordered ADT example. Ordered array list. Let's just, this is so weird. And I hate that I can't like talk to you all in person, because then I bet you see what's wrong and you're just like, this is what's wrong, Lauren. Because hello definitely ran. And down here, if I do hello, that also definitely ran. What happens if we say, I bet this is empty. Yeah, that's empty. So our insert is not working the way we want it to. For int I is equal to 0, I is less than 20, I plus plus, integer, we're getting a random integer, and then we're going to insert it right in here. Let's go back into our insert method. We say Boolean position is false. Oh, haha, I already know what's wrong. This is super funny. So when it's empty, of course, this never runs. And if this never runs, the whole thing just quits and nothing ever happened. So that's hugely problematic. I did not take care of the base case here where our list is empty. And the very first element just gets inserted right at the beginning. So right here, there's lots of different ways to handle this, but just for time's sake, I'm just going to do a really quick shorthand that says if the size is 0, so if we currently have an empty list, let's just go ahead and put that element right at the front of our list. Add at 0, there we go, add it right at the front. Otherwise, we can, pardon me, otherwise we can do this run. If we don't do this in an else, we'll end up running the for loop when we don't want to. So this situation only does this. The rest of the time, we're going to do this. And now what happens when I run it? Oh, they're all on individual lines. That's okay, but let's just fix that so that we can get a little bit better picture of what's happening here. In my print list, I say for all my objects printed out, let's get a counter going that's a spacer counter that's going to print 5 elements, 5? 4. Let's do 4 elements on a line. So it's going to keep doing this. And then spacer plus plus. And then if our spacer is 4, meaning we've printed 4 numbers, let's set spacer back to 0 and let's just print a new line. This is like the hackiest way of possibly doing printing formatting that exists. Ooh, and see, look, I don't even like how that's formatted right now. Oh, but printf can get tricky with this. Ah, no, it's fine. This, I don't like how that's formatted because they're like not all lined up nicely. So I think I'm actually going to go one step further here and format this like decently well with a space, comma, O. That should work. Should give it as a 2-string. There we go. Doesn't that look nice? So now we can actually see that they are being put in an order that we'd expect. Now, just to confirm that this wasn't just magically the order that they were like created in, we're going to also just right here at the front of our program create an array list of integers that is going to be the natural generated order of values. Array list of integers. Whoops, sorry about that. I'm right there. Move this out of the way for a sec. And then every time a number gets made, we're just going to add it to this list. so that now we're keeping like this natural order that they were created in. And then very, very inappropriately, I'm going to just copy and paste all of this code. I know it's inappropriate. I know. I'm going to copy and paste all of this code right here for the natural order generator. And I'm just going to go ahead and print and say original natural order, just so that we can have the comparison. Copy paste is so bad, but I just want to have the comparison because here we can now see that this ran in the funniest fashion. Okay, hold on. Oh, I hate that. Look what just happened. Natural order got printed there. So we're going to do our print. Let's just fix this up a little bit. \n ordered data. I would like this to not be so crazy looking. Make sure all my brackets are lining up. This one lines up here. This one lines up here. Where's my main? Oh, my main's down there. Okay, so that's fine. Okay, let me just like clear this. I'll just empty the whole thing and then I'll try to run it again so that we can actually see here. Why? Why? Natural order generator. Did I just forget to change it in here? Natural order, natural generated order, natural generated order, putting the random value in there. Oh, I wonder if something really interesting is happening here because it's like not a deep copy, an integer. This is so interesting. Like these numbers are here, but where's the rest of my ordered data? And they're all here. This is so interesting. Maybe it shouldn't be this interesting. Should I do it like that? Will that fix it? So many things I'm curious about. Yeah. Wow. Very interesting. References can be so crazy. Okay, so we take a look right here. We can see here is our ordered data in the order that we pass it in. Something funky is still happening with some of the insertions. 127, 127, 14. Like here we have a full table. And here we seem to be missing two numbers. I don't know where those two numbers went to. We're missing 197 and 194. I don't know where those went in my order data. I'm sure they are somewhere. I'm sure that they are somewhere, which is not that helpful. I wish it was more helpful. How interesting. Just so interesting looking at these things. Oh, we almost have all of our numbers there. Now we're only missing one. Random number generators are just, this is now an int. So this int here and this int here, and that should actually be fine. And these are fully separate from each other. Yeah. Oh my God. I wish I was definitely all of your instructors because then I could be like bonus points if you tell me what the heck is happening here. Because my print list is being super funny here. I don't know why it's being so funny. I want this formatting to be the same for both of them, which it now is, but there's only printing one line. Where are my other lines? Where are my other lines for each element in that list? And there's my ordered insert, and we know that the ordered insert is right. Do we? Do we know that the ordered insert is right? It could be that it's not right. We've written ordered inserts before, so this is kind of insane to me that I'm struggling to do an ordered insert. Is it that insane? It's not that insane. Let's rewrite our ordered insert just to see if that's what the problem is, because we can definitely write it in a smarter way. We can just say int index equals 0, and we can say while our index is less than our list dot size. Oops, and we should be casting, but our integer dot get at index is less than integer at O. In theory, this will work. index plus plus. So that just keeps going all the way until we hit the end. If index is the same as size, we just do a straight add. Oops. Else, are we adding them as objects? Yeah, we are. Just making sure. Else, we're going to add at the given position. Like that. Did it work? Fingers crossed, it worked. Yeah, so our ordered insert was a little bit off. I don't know why I chose to use a for loop instead of a while loop. That was super odd of me, but that's okay. We managed to solve it in the end. So we can see our order data here, and we can see the natural order is that it didn't actually get read in like that. Spent way too much time trying to get there, but that's okay. Sometimes that happens. Okay, so we actually did now manage to make that. That's great. So now you can go ahead and do the exact same thing, but for a linked list. So make a new ordered number linked list and then implement it, get it working. It should run very similar to what I just did. Only instead of an array list in the implementation, it should be a linked list. And then come back so that we can talk about ADTs and talking about ADTs and their formal interfaces. So a programming language like Java does have formal interfaces that we've seen, and we can use them to define abstract data types all the time, right? So we've already seen this with array lists and the list interface. So the list interface is our ADT, and we can go ahead and create different types of lists using that interface. So here's a snippet of Java's built-in ADT list interface. So we can't say new list, but we do declare variables of type list. Now we have seen that like capital E or T in a few different places in previous videos, and this is called generics. I'm sure you've seen it before and heard the term generics before. These can be pretty tricky to implement, and they're kind of outside the scope of this class. So we just use the big O object, which is what we've been doing, what we just did in the previous example. We worry about that. We don't worry about generics here. Now, we haven't done a ton of conversation around the big O object. What we have said is that the big O object, everything is, any kind of object is also a big O object. And it's kind of like this really big umbrella that sits on top of us, right? A big O object stands in for any kind of object. So any instance of a class can look up theoretically, and see big O object above them. It's like the sky above us. So we're all falling underneath this. So all capital letter data types, string, Boolean, integer, array list. I mean, technically list even though it's abstract. All of these data types all fall under the object umbrella, and it means that all those data types are technically types of big O object. So without getting into inheritance and the way that all of these objects are structured within each other, you can kind of just think about them how we always have, which is to say that a string is a type of object. An array list is a type of object. An integer is a type of object. A person is a type of object. That's all we're saying is they're all technically types of objects, but in this case, I'm talking about big O objects. So when we define our list interface to store a big O object like we've done, that means we can literally put any of our data types in there without any problem. And it makes it a little bit like a general list, similar to what we did with array list without those pointy brackets. So when we get an object out of our list, we're going to get a capital O object, right? Which means that the actual class is kind of unknown. We don't know what the actual class is going to be if what we get back is a capital O object. So since we don't know what's underneath, since everything is underneath that capital O object, we don't know if it's a string or a Boolean or a student. We can't call getGPA if it doesn't have a getGPA method. We can't call .length if it doesn't have one. Or what we just saw, we can't call a .compare2 if it doesn't have one. So we cast our objects. So I did just show an example of casting an object, and I said that if I don't do proper error checking, I was going to get all sorts of errors. And we can see exactly here what that means. If we're not certain that the object that we got from the list is the type that's expected, our program will crash, and we will get a class cast exception because we're trying to cast to a class that is incorrect. So let's make an object list interface as we did, and an order number array list under it using an array list of integers. So this is where I just was a little bit, my example was a little bit ambitious. Rather than doing an array list of integers, I made mine right here, an array list of objects. I should have made it integers, and then I wouldn't have had to worry about doing this casting right here like I did. But it was fine that I did that in the end. It didn't have to be a big deal. So this is object list example.zip. We can actually go ahead and rename this folder here to be that. I will rename it to be object list example. Now, we did just talk about doing the safe casting. How to safely cast an object is to check the instance of it. I showed it as both an if statement and as the ternary operator and what we would do to do so. So the instance of operator produces a true result if it actually is that kind of class and false otherwise. Now, a better strategy than what we did is to make a generalized list of objects and then build something on top of it. So first we make our object list that we already have, that it holds an array list of objects or whatever it is. But then on top of that, we build a wrapper for a string list or an integer list or a person list so that we can utilize the same code that's inside object list, but then around it, we can ensure that only strings get stored in that one or only integers get stored in the next one or whatever. And we can see that we don't have to worry about safe casting then, because here we're only adding strings and here we're only going to be passing back strings. So it does add another layer to our like code structure. However, it does help us with the problem that we saw with instance of and class cast exceptions. So that part is pretty nice. Now, this is basically already what we were doing when it came to wrapping an array list of people into a method or into a class called person list, right? We were already doing that. The main difference here is that we are creating an object list and then we're wrapping that in a string list. So we see ourselves wrapping our own code in another class as opposed to just wrapping Java's array list code in a class. But this really isn't something new. We've already been doing this. Now, we did already say we can't make an ordered list out of objects, but we could make it out of, which I attempted to do as we just saw, but we can make it out of comparable. So this is another way to solve the problem that I was just having. So let's go back and do that. I should have known better. I should have known better, but that's okay. This is all learning. Rather than this being object, we're going to pass in comparable. Anything that is comparable can be stored in an ordered list. That makes a lot of sense because then we can actually order it. So these are all going to take in comparable. Again, we're not going to worry too much about the T part of that since we're not going to be dealing too much with generics. We can suppress warnings if we want it to go away. See, suppress warnings, but you'd have to do that on everyone. It gets very messy. It's okay, don't worry about it. It does mean that now this ordered list, array list, implementing order list. This can't be object. This needs to be comparable. This can't be object. It needs to be comparable, comparable, comparable. Now, if this is comparable, I no longer need to cast this. It's unnecessary because I can just say dot compare to. And we know that compare to is a thing that exists. And that should actually just be okay now, is undefined for the type object. Oh yeah, I just haven't, it's because I haven't finished changing all these spots yet. Comparable, and comparable and comparable. That was really why that was still a problem. I just missed those. So right there, we can see the method compare to is there. The only reason it's yellow is again because of the generics things. So that's much better now. These are all using comparable now. And this doesn't have to change because here we are creating integers and passing in integers. And we know that integer implements the comparable interface. So now that code actually works. I guess I could run it with this fixed problem. I spent so long trying to fix that problem there, and had I remembered that we can just use comparable, I wouldn't have had to worry about casting from object. That was so silly. But that's part of the learning experience. It's okay. So since we don't use comparable, we don't use generics, our comparable class drops that bracket class name part at the end of it. So like object, we would end up, in order to like get rid of those yellow squigglies, we would want to be casting things properly. And within our insert, we're also going to want to make sure that we're doing our proper call to compare to determine our order appropriately. And depending on the type of object it is, we might need to do some casting. Now, the order list can be implemented with an array list, with a linked list, whatever it is, anything as long as it's got comparable objects inside of it, this is going to work. So there are many other abstract data types that are used to solve these kinds of problems in computer science, and we're going to take a look at two of them. We're going to look at stacks and we're going to look at queues. Now, both of these are going to come in a separate video, each of them showing the implementation of these two different types of abstract data types. So meet me over at those videos when you're ready to take a look at those. And until then, thank you, everyone. This has been our first introduction to abstract data types.